today. So this is our lecture for strength of materials. So if you are to discuss some of the topics of strength of materials, we may start with stress. Basically, stress is equal to the force divided by area. So we have several types of stresses. Let us have first, let's say this is the normal stress. Let us use a sigma as the normal stress equal to the applied force divided by the area. So if we say normal stress, basically the applied force should be perpendicular to the area. So just like this example, so a solid circular steel column is to be designed to carry an axial load of 620 kilonewtons. So if the allowable axial stress is 46 megapascals, what diameter of column is required? So for example, this is our column to carry the given load, P, and this is the area. So it is assumed that the applied force should be perpendicular to the area and the stress is uniformly distributed to the cross-section of the column. So this is an example of a normal stress. So we have a load equal to 620 kilonewtons and the allowable stress is equal to 46 megapascals. So we are computing for the diameter of the circular column. So again, for normal stress equal to the force divided by area. So you have the allowable stress equal to 46 megapascals. And 46 megapascals is the same as newtons per square millimeters. Equal to the load, this is the same as 620 multiplied by 1000 newtons. So let's have it in terms of the unit newtons divided by the area of a circle in terms of the diameter, pi d squared divided by 4. So we are looking for the diameter. So we have that 620 divided by 1000 divided by 46 divided by pi over 4 square root. So we have 131.0002. Well, let's have it as 131 millimeters. So on our choices, that is letter D. And so let's have another type of stress, that is the shearing stress. For shearing stress, we have it as tau, that is the same as the force divided by area. But for this case, the applied force is parallel to the resisting area. Okay, so the force is parallel to the area. So just like this example, what force is required to punch a 20 millimeter diameter hole through a 10 mm thick plate? The ultimate strength of the plate material is equal to 450 megapascals. So for example, we have a plate. And let's say this is the thickness is equal to 10 millimeters. We are to punch a hole. So say we have this P. The diameter of this hole should be equal to 20 millimeters. So if we are to observe, for example, the removed part from this plate is like a small cylinder. So the height of the cylinder is the same as the thickness of the plate, which is 10 millimeters. So this is the direction of the force. So again, if you are dealing with a shearing stress, you are to consider an area that is parallel to the direction of the force. So if this is the force, the resisting area is the same as the lateral area. And the lateral area of this removed cylinder from the plate. Okay? So again, its diameter is 20 millimeters. If we are to observe what is this is our area this time. Right, the lateral area, that will be the area under consideration for this case. So what will be our area? Okay, that is a lateral area of a cylinder. If we are to spread that out, that is the same as a rectangle having a height of 10 millimeters, and its corresponding length is the same as the circumference. So circumference is the same as pi times the diameter. So the length or the circumference is pi times the diameter of the hole, that is the same as 20 mm. So we'll be having a length of 20 pi millimeters. Okay, this is our area. So again, we have the equivalent of tau. The tau is equal to the force. This is divided by area. What is our strength? The ultimate strength of the material is equal to 450 megapascals. I'll be right here. Okay, so we have tau is equal to the force divided by area. What is the ultimate strength of the material? Let's have it as 450 megapascals or newtons per square millimeters. The applied force divided by, what is our area this time? It is an area of a rectangle. The 10 millimeters thickness and the circumference of this hole of the plate, that is 20 pi. So 20 pi, that is the length of the rectangle multiplied by the height. This is multiplied by 10 millimeters. So this will be the same as mm squared. 20 pi millimeters times 10 millimeter. So if we are to observe, cancelling squared, this value of P is now in terms of newtons. So we have that as 450 multiplied by 20 pi times 10. So we have that as 90,000 pi, or in kilonewtons, that is 90 pi or 282.743 kilonewtons. So 282.743 kilonewtons, and our choices, we have that as letter B. Next up, we are to discuss strain. So we are using the symbol epsilon. So basically, we say strain, that is equal to the ratio of the deformation. This is divided by the length of the structural member. So delta over the length. So if we are to, what is the relation between stress and strain? Basically, stress is directly proportional to the strain. Okay, so for an equation, stress, we have to place a proportionality constant multiplied by the strain. Wherein the equivalent of this proportionality constant is the E. This is the same as the modulus, and the modulus of elasticity. So if we are now simplify the relation, stress is equal to the proportionality constant times the strain. We have the stress is equal to the modulus of elasticity multiplied by the strain. What is the equivalent of stress? This is for a normal stress, that is the force divided by the area. I want it equal to the modulus of elasticity. Equivalent of strain, that is the ratio of the deformation over the original length. So if we are now computing for the deformation is equal to the force times the length divided by the area multiplied by the modulus of elasticity. This is our formula for axial deformation. So let's have an example. Okay. For this example, so a mild steel column is hollow and circular in cross-section with an external diameter of 350 mm and an internal diameter of 300 millimeters. So we are just to consider the solid part to carry the load 2000 kilonewtons. So it carries a compressive axial load of 2000 kilonewtons. So which of the following gives the shortening of the column if its initial height is 5 meters? So this is the delta deformation is equal to the axial load, the length divided by the area times the modulus of elasticity. So usually for civil engineering board exam, there are cases that the modulus of elasticity is not given. But for the case of steel, it should be known as E equal to 200 gigapascals. Alright? So our area will be the same as, since it is a hollow outer area, or that is the area of the outer circle minus the area of the inner circle. So we have delta, what is our axial load? So let's have it as 2000 multiplied by 1000 in terms of newtons. And multiplied by the length, we have that as 5 meters or 5000 millimeters. This is divided by the area. What is our outer circle? That is equal to 350 mm, 350 squared pi divided by 4 minus inner, that is we have 300 squared pi divided by 4. So obviously this unit is millimeters squared. So this is multiplied by 200,000 megapascals. So let's have it in megapascals. Megapascals is the same as newtons per square millimeters. So if we are to do unit analysis, so we are to cancel mm squared and the newtons. So the remaining unit, since it is a shortening, obviously since a compressive load, or it is a deformation, it should be in terms of mm. So let's compute for that. So we have 2000, or this 2 million kilonewtons. So we have it as 959 millimeters. So on our choices, we have it as 1.96 mm. So our answer will be letter C. So let's have an example. For example, you have a member that is carrying multiple axial force. So the aluminum bar shown has a uniform cross-sectional area of 350 mm squared. Modulus of elasticity of aluminum is 69 gigapascal. So which of the following gives the total deformation? So before we proceed for the computation, we should first determine the net axial force per segment. It is wrong to assume that 1.6 meters segment is carrying 25 kilonewton, the 1.2 meter segment is carrying 10, 1.8 is carrying 5. No. So we need to determine the net axial force per segment. So for that procedure, we may use the load diagram. Okay, but first, we may determine what is the reaction on the fixed support. So that is, by summation of forces, horizontal equal to 0, to the right forces to be positive. So I'll be assuming that the reaction is to the left. So that is, we have 25, okay, minus, this is 10, minus 5, minus the reaction, equal to 0. So we have 25 minus 15 is 10. R, yes, positive 10 and transpose. We have R is 10 kilonewtons and its direction is, okay, it should be to the left. And this is equal to 10 kilonewtons. As you can see, this is obvious, 25, 10, 15. So now we are to observe, okay, what is the effect of 5 kilonewtons to the member? That is a compressive force. It compressed the member. So we assume that to be negative. So this is, okay, for the load diagram, we are starting on the right end. This is negative 5. Negative 5, the same direction as the 10 kilonewtons. So we add the two. That is negative 5 plus negative 10. Okay, we'll be having a magnitude of negative 15. Okay, so this is negative 15. So on this point, we have 25 kilonewtons to the right. That is, its effect to the member is tension. So that is positive. So 25 plus negative 15 is positive. Okay, we have positive 10. Then we have our reaction. That is 10 kilonewtons to the left. That makes the value 0. If we have to add negative 10 plus 10 kilonewtons. So what is the advantage of load diagram? So we know the portion of the segment which are under compression or under tension. If we have them as negative, this portion is under compression. Under compression, if this is positive, this is under tension. So we will compute for the total deformation, that is the summation of PL divided by the area. Okay, but since we have constant area and the modulus of elasticity, we may have it as 1 over the area times the modulus of elasticity multiplied by the summation of the force times the length. So, okay, we are to carry the signs. Negative for compression, positive for tension. So let's have it as the total deformation is equal to 1 divided by, what is the area of the aluminum rod? We have 350 millimeters squared. And then we have the modulus of elasticity, 69 gigapascals. Let's have it here. We have the total deformation is equal to 1 over the area, 350 millimeter squared. Okay, the modulus of elasticity is 69,000 megapascals or the newtons per square mm. And this is multiplied by what is our load here? So we have for the segment 1.6, that is 10 kilonewtons. Positive 10 kilonewtons multiplied by the length, we have that is 1.6 meters. Okay, plus the next segment, which is under compression, we have a magnitude of negative 15. So this is negative 15 kilonewtons. What is the length of the segment? That is 1.2 meters. Okay, plus our last segment, a 1.8 meter segment with a magnitude of negative. This is negative 5 kilonewtons with a length of 1.8 meters. So if you are to do unit analysis, it's kilonewton meter multiplied by 1000 squared to be in newton mm. Alright, let us compute for the total deformation. So we have that as the first segment, that is 10 times 1.6, positive since it is under tension. Then minus 15 times 1.2 under compression, minus 5 times 1.8 also under compression. So we have to multiply it by 1000 squared for the unit to be in newton mm. Then divided by 350 divided by 69,000 megapascals. So the remaining unit will be in terms of millimeters. So we have that as negative 0.455 mm. So the negative means, the negative sign means I will be having more compression or more shortening more than elongation. So on our choices, okay, negative 0.45 mm, and our choices it is letter B. So let's have this example. So also a previous board exam problem for civil engineering. So the hammer for each chandelier in the grand ballroom of a 5-star hotel is composed of 2-meter diameter ring weighing 2.5 kilonewtons per meter. And is supported by 6 rods such that the said ring will be 3 meters below the ceiling support. So which of the following most nearly gives the vertical displacement of the ring if the diameter of each cable is 10 mm. So this will be the setup. So let us first determine what is the total weight of the ring. The total weight is, we have, that is 2.5 kilonewtons per meter. And we are to multiply it by its circumference. That is the same as the total length of this rod material used to create the ring. So what is the circumference? Having a diameter of 2 meters, that is the same as pi d. Pi times the diameter, so pi times 2 meters. So we having the total weight of the ring as 2.5 times 5 times 2 as 5 pi kilonewtons. That is the total weight. So this time, we are just to consider one of the rod or cable. Then let us have our free body diagram. So considering one, and let us form triangle for the, let's have a force triangle. So let's say this is the tension for one cable. The weight is downward. Okay, so let us, if you are to observe the dimensions, this is initially 3 meters vertical. This is 1 meter, that is the radius of the circular ring. Then this will be, what is our hypotenuse? So that is 9 plus 1, 10. That is the square root of, okay, we have square root of 10 meters. So we can determine the tension for each cable by summation of forces vertical. Since we have 6 cables, this is multiplied by 6 again. Since we have 6 cables. So by summation of forces vertical equal to 0, apart forces to be positive. What is the vertical component of the tension? That is 3 over the square root of 10. So we have 6 times the tension. Vertical component is 3 over the square root of 10 minus, what is the total weight of the ring? We have 5 pi kilonewtons equal to 0. So let's have the tension per cable. Okay, the tension per cable is 5 pi divided by the square root of 10, that is divided by 80. So we have that as 2.796, or let's say 2.76 kilonewtons. So again, we are using 6 rods. We don't have the type of material. So we assume this to be a steel with modulus of elasticity 200 gigapascals for steel. So obviously, what will happen? There will be a deformation on these cables. So let us determine the deformation of the cables. So we have delta is equal to the load, the length divided by the area times the modulus of elasticity. So let's say this is the deformation of the cable. Let's say delta C. And we have, this is okay, we have delta C. What is the axial force per, or the tensile force per cable? We have 2.76. This is multiplied by 1,000 to be in newtons. What is the length per cable? The length per cable is square root of 10 meters. So this is multiplied by the square root of 10 multiplied by 1,000 to be in millimeters. So divided by the area. What is the cross-sectional area of each cable? We have a diameter of 10 mm. So this is 10 squared pi over 4 millimeter squared. So there are cases in our board exam that E is not given, but if it is assumed to be a steel, we have 200 gigapascals or 200,000 megapascals, or the newtons per square mm. So let's have the deformation or elongation per cable. So we have 2.76. So we have a deformation of 0.556 millimeter. So what will be the vertical displacement of the ring? If there will be an elongation of 0.556 millimeter on each cable, so obviously, if these cables will be elongated, the ring will go down. So if you are to draw that, so this is the same as the square root of 10 meters, the square root of 10, the initial length of the cable, plus the deformation due to the tensile force on each cable. So we have, initially the height of this, or the distance from the ceiling to the ring is 3 meters. But this time, you'll be having 3 meters plus the vertical displacement. So let's say this is delta B. But by the way, the radius of the circular ring will remain as 1 meter. So how to compute for that delta B? We can have it by Pythagorean theorem. So basically, still there is a right triangle. So by Pythagorean theorem, what will be our equation? The hypotenuse is the square root of 10 plus delta C is equal to, we have 3 meters plus the vertical displacement of the ring squared, okay, plus the 1 meter squared. So all you have to do is substitute. So this is the same as the square root of 10 plus, what is the deformation of each cable? That is equal to 0.556. This is in terms of millimeter divided by 1,000 to be in meters. We have it as square. Then, this is equal to, we have 3 meters plus delta B. This is divided by 1,000 to be in, so that our answer will be in terms of millimeters squared plus 1 squared. So let's compute for the vertical displacement of the ring. So you have square root of 10 plus 0.556 over 1,000. And that quantity is a squared minus 1. Okay, then square root minus 3. Multiplied by 1,000. So we'll be having an answer of delta B equal to 0.586 millimeter. Okay, so on our choices, so 0.586, so the nearest value is letter C, 0.59. What's this value? And we have 0.59 mm. So let's discuss spring. So for example, we have this spring carrying a load P. Let's say the diameter of the spring is 2r, or it's the same as twice the radius. So we are just to consider, let's say, a portion of the wire used for this spring having a diameter of D. So we are required, for example, to compute for the shearing stress experienced by the spring in carrying this load P. The shearing stress is basically shearing stress due to torque. That is the torque multiplied by the radius divided by the polar moment of inertia. This is due to the torque, plus the other is direct shear. What is direct shear? It is basically the force divided by area. So if we are to discuss some of the terms in this equation for direct shear, this is combined shear. So we have the torque is a twisting moment ay caused by this force P at a distance r, the radius of the coil. The torque is basically the force P or the load P multiplied by the radius of the coil. While our small radius r, this is the radius of the wire. That is the small, the radius of the wire or the small diameter. We have that is diameter divided by 2. What is the polar moment of inertia of this cross-section of the wire? Polar moment of inertia is pi, the diameter raised to 4. This is divided by 32. The polar moment of inertia of a circular section. So what is the cross-sectional area? Basically, the cross-sectional area of the wire is pi diameter squared divided by 4. So we have now the total shearing stress experienced by the wire of the spring is the torque, that is the load times the radius of the coil, multiplied by what is equivalent of the small r, that is the diameter of the wire, divided by 2. Divided by the polar moment of inertia, that is pi, the diameter of the wire raised to 4, divided by 32. Plus the direct shear, the force over area, that is P, divided by the cross-sectional area of the wire, that is pi diameter squared divided by 4. So we have now the total shearing stress. The total shearing stress tau is equal to, we have 32 over 2 is 16 times the load. The radius, we may cancel one of the diameter of the wire, so this is now raised to 3. That is divided by pi, the diameter raised to 3 plus, this is the same as 4 times P divided by pi diameter squared. Okay, so we can simplify this one similar to what is available in our references. If we have the tau is, we factor out 16PR divided by pi, the diameter raised to 3. This is now 1 plus, we have this is the same as the diameter of the wire. I divide by 4 times the radius. So if we are to check that, we have 16PR divided by pi d cube multiplied by the diameter divided by 4 times the radius equal to, we may cancel the capital R and the diameter. So what is 16 over 4? That is 4 times 16 over 4 is 4 times P. I divide by pi. We cancel one of the diameter, d squared. The same as this one. So this equation is applicable for light springs. So what about if we have heavy springs? If for heavy springs, we are to use the wall formula, wherein we need the spring index. In some references, they are using C. In some references, they are using the value of M. This is the same as twice the radius, that is the same as the diameter of the coil divided by the diameter of the wire of the spring. So we will be having the shearing stress as 16P times the radius of the coil divided by pi, the diameter raised to 3. This is multiplied by 4 times the spring index minus 1 divided by 4 times n minus 4. This is plus. We have 0.615 divided by the value of m. So this equation is applicable for heavy spring. And according to some references, more accurate compared to the other equation. So let's discuss for the deformation of a spring. Basically, we are to recall the formula from torsion. That is the angle of twist. It's equivalent of the angle of twist. We have theta is basically equal to the applied torque, the length divided by the polar moment of inertia times the modulus of rigidity. So if we are to compute for the equivalent of the delta, delta is the same as theta times the radius of the coil. So what will be the total length of the spring? The total length of the spring, we need the number of turns. So basically, we need the number of turns. How many coils are there in this spring? So how to determine the length of the spring if you are to stretch this spring? That is the number of turns. Multiplied by the, let us consider one circular portion of the coil, multiplied by the circumference. What is the circumference in terms of the radius? That is 2 pi r. That will be the total length of the spring. Okay, then what is our polar moment of inertia? That is pi, the diameter raised to 4 divided by 32. So from theta is equal to the torque, the length divided by the polar moment of inertia times g. We are to multiply both sides of the equation by the radius of the coil. So what is r theta? That is the delta, the deformation of the spring. This is the same as an arc. Okay, the length of an arc. So this is delta. What is the equivalent of the torsion a while ago? The torsion is the force P multiplied by the radius of the coil of the spring. What is the total length of the wire used in the spring? That is the number of turns multiplied by the circumference of one circular coil. So it's multiplied by 2 pi times r times the number of, that is the number of turns multiplied by 2 pi r, then multiplied by again by the radius. This is divided by polar moment of inertia. We have pi, the diameter raised to 4. This is divided by 32 multiplied by the modulus of rigidity. That is 4g. So if you are to simplify, we have now the deformation of the spring equal to, we have 32 times 2. That is, we have 64 times p. Times p. 64 times p, r times r times r is r cubed, number of turns, or that is the number of circular coil, divided by the modulus of, we may cancel pi. That is divided by the modulus of rigidity, the diameter raised to 4. This is the formula for the deformation of a spring. So 64 times the load P, the radius of the coil cube, the number of turns, all over the modulus of rigidity times the diameter of the wire raised to 4. So let's have an example. So let's have this example. So a helical steel spring composed of 20 turns, 20 mm diameter wire on a mean radius of 90 mm. When the spring is supporting a load of 1.5 kilonewtons and G is equal to 83 gigapascals. So determine the total shearing stress in the spring. So we don't know if it is a light spring or a heavy spring. Let us first assume as a light spring. If it is a light spring, the shearing stress equal to 16 times the load, the radius of the coil divided by pi, the diameter of the wire raised to 3, is multiplied by 1 plus the diameter of the wire divided by 4 times the radius of the coil. So let us substitute. We have a shearing stress equal to 16. What is our load? That is 1,500 newtons. The radius is 90 millimeters. And this is divided by pi. Diameter of the wire is 20 millimeters. This is raised to 3. We have multiplied by 1 plus. Diameter of the wire is 20 divided by 4 times the radius, that is 90 mm. Okay, so as you can see, this is the same as unitless, this portion. So let us compute. We We have that as 16 times 1,500 newtons multiplied by 90 millimeters. This is divided by pi divided by 20 raised to 3. Multiplied by 1 plus 20 over 4 times 90. So we have that shearing stress is equal to 90.718. This is cancelling mm, so this is the same as mm squared. Newton per mm squared is the megapascal. So do we have this one? So as you can see, we don't have that value on our choices. So let's try if it is a heavy spring. For the heavy spring, we need the value of the spring index m. That is the same as twice the radius of the coil divided by the diameter of the wire. Or basically the diameter of the coil divided by the diameter of the wire. This is twice of 90 divided by 20. So we have that as 9. So for heavy spring, we are using the Walsh formula. We have the shearing stress is equal to 16 times the load, the radius, divided by pi, the diameter raised to 3, multiplied by 4 times m minus 1, divided by 4 times m minus 4, plus 0.615 divided by the value of m. So let us substitute. We have now the shearing stress equal to 16 times 1,500, the radius is 90, divided by pi, the diameter is 20, diameter of the wire, multiplied by 4 times 9 minus 1, divided by 4 times 9 minus 4 plus 0.615 divided by 9. Computing for the shearing stress, considering it is a heavy spring. So we have that as 99.87. We have 99.874 megapascals. So let us check on our choices. We have letter A, that is 99.87.